there's nothing we can try to do to explain what experience really is. The experience itself, the way these neurons are coding what we see or hear or think or feel, we don't know how to deal with that.
Welcome to Closer to Truth. I'm speaking with Professor Marcelo Gleiser, physicist, cosmologist, and science culture visionary, about his important new book, The Blind Spot: Why Science Cannot Ignore Human Experience, written with Adam Frank and Evan Thompson. Welcome, Marcelo. I've looked forward to speaking for a long time. We have so much in common. Congratulations on The Blind Spot.
My pleasure, and same here. I've been looking forward to being part of this for quite a while, so I'm very happy to be here.
Great. Now we're going to talk about the blind spot in depth, but I really want to start with some really breathtaking discoveries of the James Webb Space Telescope, and we've been following it for a while. We see galaxies larger earlier than expected, more structured in the early universe. Some galaxies less than 500 million years after the Big Bang, within 4% or so of the 13.8 billion years of the universe, huge black holes. And literally just this morning, I was reading a report of the latest galaxy that was the size of, bigger than the Milky Way in terms of numbers of stars. And it was, the galaxy itself was 11.5 billion years ago, but the spectrography of some of the individual stars that they were able to discern, or the character, brought it to within 800 million years, or 13 billion years ago. And the comments made, at least preliminarily, of the standard model of cosmology, which requires a sufficient clumping of dark matter in order to form these galaxies, wouldn't have been able, at least under the current structure of the Big Bang standard model. What's your sense of all of this?
So my first reaction is excitement, because clearly there's something missing in the picture, as you have said, and we just don't know what it is. It could be something as boring as we really don't have a good model of galaxy formation yet, and it may be that galaxies form much more efficiently than we think they did. It's sort of like if the universe is in a hurry to grow up, right? And so everything is happening much faster than you would expect. You know, at some point, I kind of equated what's going on to having the grandparents, the kids, and the grandkids all coexisting much earlier than we thought they would. You know, and so these generations are sort of getting kind of confused with one another. And honestly, I wouldn't panic yet in terms of, oh, everything is wrong and we have to rethink things deeply, because we are not at the level of truly understanding the formation of galaxies as well as we would like to. However, you know, we should always keep in mind that experiments drive discovery, and this is exactly what's going on here to a large extent. And the fact that what we thought was our standard model of cosmology may not be as standard as we thought, could be an open door to new ideas. And there are quite a few out there, but certainly the old cold dark matter scenario may need some revision.
So to be clear, in terms of our standard model, we generally think of it in two broad parts. One is the so-called origin cosmic inflation theory, which terminates in the so-called Big Bang, and then the lambda cold dark matter model for galaxy formation. This would be a potential challenge of the latter, at least as far as the dark matter is concerned.
Yeah, in a sense, in order for structure to grow, for galaxies to grow, you need to clump matter together, right? And the way we've been doing that is by using cold dark matter clumps that would then attract what we call baryonic matter, which is the stuff that we are made of. And then you have stars forming, and then eventually the stars coalesce into galaxies. And so what seems to be the problem is that too much stuff is getting clumped too quickly as to accelerate the formation of these early galaxies. And that puts into question the efficiency of the cold dark matter scenario to do this very fast clumping. And so the question is, how could we accelerate the efficiency of that process? Could it have started earlier than we thought? And we don't know the answer to that yet.
So one possibility has to do with the characteristics of dark matter itself, which of course we don't know what it is, lots of theories, but
Right.
In terms of how the dark matter clumps together, because the current theory requires it to have what 1 or 2 billion years of interactions in order to have sufficient clump to build a galaxy. So that might be the part. Or is it more radical that maybe something other than dark matter is causing the clumping, or that's much more unlikely?
Well, that's the terrain of speculation, right? I mean, we don't know. And I'm very, very careful when it comes to that. And it may very well be that what you first form is these gigantic stars. Those gigantic stars create gigantic black holes very quickly because very massive stars are very unstable. They live very, very shortly compared to, say, the sun. And when they go, they leave behind a massive black hole, very, very big black hole, that then acts as a catalyst for more matter to clump. So you have like the dark matter background plus those giant early black holes that can be sort of like a giant maelstrom, like just bringing stuff in much faster and more efficiently. And that may be what's missing in the picture. Some people are beginning to think in those ways. It's not just dark matter, but these big black holes are catalyzing the process of early galaxy formation.
Yeah, that makes sense, and it's certainly an alternative possibility or an enriching possibility that enables us. What I've seen is, at Closer to Truth, we get a lot of people sending us their theories, and I've sort of said that there's a new cottage industry that is being born that challenges the traditional standard model in cosmology, even as far as the speed of light, so-called tired light, and challenges the Big Bang itself and inflation theory and all of that. And people use an individual piece of data like we're discussing now that just was discovered as the way to blow up everything and start from scratch, even back to a standard state model.
Yeah, I wrote an op-ed for the New York Times with Adam Frank, which is a co-author in the Blind Spot, and it was a bit of a provocative piece. It came out, I don't know, September or October last year, saying, is our current cosmological models beginning to unravel? Right? I mean, is it in trouble or not? And one of the things that we said is that, in broad lines, it works very nicely, but perhaps in more detail, it won't. And the question is, how do you fill in the blanks? I mean, is it true, same physics, but understood in different ways? For example, big black holes forming early, and like, or is it new physics? Is it because we don't really know what dark matter is doing and what it is, and could it have been acting earlier than we thought? And that's possible. So that's why my first reaction when you brought this up was, it's exciting. Crisis is not a bad thing in science. It's actually a good thing in science because it forces us to think outside the box. Right?
Well, I'd look forward to our continuing to discuss this as new data comes in over the next months and years. So we'll follow it together. Let me give a better and a longer, although still brief, bio, and then we can get into your books. Marcelo Gleiser is a theoretical physicist and public intellectual at Dartmouth College, and his research ranges from cosmology and applications of information theory to complex phenomena, to history and philosophy of science, and how science and culture interact, all of which we'll be discussing. In 2019, he won the Templeton Prize for being a leading proponent of the view that science, philosophy, and spirituality, which we'll discuss, are complementary expressions of humanity's need to embrace mystery and the unknown. So, Marcelo, to prepare for a thorough discussion of the blind spot, let's briefly, very briefly, review your prior books, because as I looked through them, I read The Blind Spot, which is a terrific book. I recommend it for everybody, but skimmed the previous books. But I sensed an intellectual arc of your developmental thinking. And I'd like to give the structure of that first, again, very, very briefly. So the first book, as I see it, was A Tear at the Edge of Creation, The Simple Beauty of the Unexpected. What was the theme?
So A Tear at the Edge of Creation is a book I wrote, wow, quite a while ago, like 2010. And it was a criticism of the prevalence of the idea of symmetry as beauty in theoretical physics.
Mm-hmm.
And you have spoken to many people, like colleagues of mine, like Frank Ochak and a bunch of others, that say that beauty and symmetry are equated in our quest for understanding how nature operates, right?
Right.
And there is a profound appeal, and of course, it's very understandable why that happens. First, because symmetry simplifies things. And second, there is this very old Platonic tradition in physics where the idea that mathematics is synonymous with truth and beauty are equated, just like John Keats, poem, right? And that if we uncover the symmetries of the world, we can then discover the blueprint of creation. So a lot of the history of modern physics, and I'm sure you have uncovered this many, many times. In fact, I watched some of the programs where you discuss these things with some of my colleagues and predecessors, where that's what we have to do. Look for the symmetry, and then you'll find the answers. And what this book does, A Tear at the Edge of Creation, does is it tries to deconstruct this idea and say, but wait a second, because if you really look at what's going on, it's really asymmetry that is the fundamental building block of reality. It's because just by definition, when you have a system in equilibrium, a system which is balanced, nothing happens, right? It's the imbalance, the disequilibrium that prompts motion, that prompts change. And if you look at the particle physics, there are some fundamental asymmetries that are absolutely essential for us to be here. The most important of them is the asymmetry between matter and antimatter, right? So if there were equal amounts of matter and antimatter in the universe, most of the universe would just be radiation, a bunch of photons, and we wouldn't be here. So there is an imbalance. It's 1 part in a billion of more matter than antimatter. And myself and a bunch of other people spent the 90s working really hard trying to figure out where is this matter antimatter asymmetry come from. And we still don't have an answer, but we have a fact. This is how it works, So, and without that, basically the universe would be a very different place. So that's one. And then more technically, there are all these other symmetries in particle physics called charge conjugation or charge invariance and parity invariance. And those are all violated. Those symmetries are violated. And there is the time asymmetry, the fact that time really moves forward. And maybe you have heard people say time doesn't exist, but I am actually a defendant of the fact that time exists. Every time I look in the mirror in the morning, I kind of realize that, I'm sorry, folks, it's changing, it's happening. So time asymmetry is another very important one, and that connects with cosmology because it tells you something related to entropy, which is that the universe needs very specific initial conditions in order to become the universe that it is today, which is it needs to be in what we call a low entropic initial state, which means an ordered state in order to then become less ordered, more disordered as time goes by. And that's related to the asymmetry of time. which, by the way, we analyze a lot in detail in the blind spot.
Good. We'll get to that. And in terms of the asymmetry,
Yeah,
you both need a symmetry to understand particle physics, and then the violations of it, the asymmetry to enrich that. So you really need both as part of a fundamental aspect. And I think what you're saying is that you are emphasizing the asymmetry because most people use the symmetry as the demonstration of ultimate truth.
right. And even the symmetries have to be broken. So we talk about breaking of symmetries in order to explain, for example, how particles have mass. So the discovery of the Higgs in 2012, one of the things that this Higgs field does is that it gives mass to all the other particles. And in order to do that, the so-called symmetry that existed early in the universe needs to be broken. Just like when you freeze water, you're breaking, symmetry as well, because liquid water has an equal probability of finding molecules everywhere. And when you freeze it, you don't, because you form a crystal. So in between the molecules, there is nothing. Well, um, so so yes, and then there's a second part to the book, which I think is even more interesting, which is beyond physics, which is biology. That life is also asymmetric in the sense that if you look at how proteins are made, so proteins are made of amino acids. And this is something that Louis Pasteur discovered in the 1850s in France. Of course, being a good French, he was studying wine and fermentation of grapes. And he discovered that the molecules of life, all the biomolecules, when you generate them, when you make them, synthesize them in the laboratory, they have this property called chirality, like your hands, left and right hands. You cannot superimpose your left hand and your right hand. So that's called chirality. One is the mirror image of the other. These biomolecules are also like that. So when you synthesize them in the laboratory, those amino acids come 50% left-handed, 50% right-handed. However, in every protein of pretty much every or most living systems, every amino acid is only left-handed. And
Okay.
so
Yeah.
you know,
Finish. Yeah.
yeah, I was just going to say, and the question is, why did life selected a single-handedness for these biomolecules? And we don't have an answer today yet. And I also have done a lot of work on that, trying to figure out that.
Okay, let's go to the island of knowledge, the limits of science, and the search for meaning. And those are very rich, closer to truth kinds of subjects.
So the island of knowledge metaphor is the basic idea that let's imagine that all the knowledge that we have of the world, of ourselves, and it does not need to be just scientific knowledge, it could be any kind of knowledge, fits in an island, right? And of course, as science progresses and knowledge progresses, this island grows. But as with any good island, the island of knowledge is surrounded by an ocean, and the ocean has to be the ocean of the unknown. So the idea here is that as knowledge grows, it is covering a bigger area of this ocean of the unknown.
Yeah.
And then there are two ways you can go with that. Say, aha, wonderful, right? Because as you know more about the world, there is less for us to know because we are getting, less and less of the ocean of the unknown. That position, which sometimes is called scientism, is philosophically incorrect for the following reason. As the island grows, so does the boundary between the known and the unknown, the periphery of the island, which basically means the following, that as we learn more about the world, we become equipped to ask questions that we couldn't even have imagined before, because new knowledge generates new questions, right? And two very canonical examples of that is one, the invention of the telescope, right, in the early 1600s. Astronomy before and after the telescope are completely different things. The other one in the same century is the invention of the microscope. In what is life? And this has happened, throughout the history of science with the invention of more instruments. I call them reality amplifiers that allow us to see more but also allow us to ask questions. And hence, this is the idea that knowledge is, as far as we get funded, knowledge is, at least scientific knowledge, is unending. And we can discuss what I mean by that later.
So the metaphor in terms of the ocean of the unknown is epistemological in the sense of our capacity to ask the question to know what the unknown is. It's not ontological, because ontological is the way it is, irrespective of human existence or understanding. It was always there, but it expands from our own sense of what it is. So it's epistemological, not ontological, right?
Yeah, and it's a little subversive, a little, because it puts ontology after epistemology, which
Mm-hmm.
some philosophers can be a horrible thing, because
Right.
basically what I'm, and that connects with ideas we'll talk about soon, which is that you cannot know the world until you interact with the world, and that knowledge is essential. So, in the way you interact with the world depends on the way you see the world through your instruments, and that is limited. And I have to quote this guy because you're going to love it if you don't know it. So, this French philosopher Bernard Le Bovier de Fontenelle, who in 1686, the same year that Newton wrote the Principia, he wrote a book called A Conversation on the Plurality of Worlds.
Mm.
Magnificent book. Freeman Dyson wrote the preface, one of the editions. But the reason I quote him is because at some point he has a protagonist that asks him a question, the philosopher that is trying to talk about life in other worlds, and asking what is philosophy. And philosophy here means natural philosophy, science. And he says, all philosophy could be summarized in this way. It's a compromise between curiosity and short-sightedness.
That's wonderful.
Right? Because we want to know, of course we do, but we can't see everything. And so from the tension of wanting to know and not seeing everything comes philosophy and science. And I think that's right on. And it summarizes things quite well.
Right. You mentioned a number of specific kinds of things that are limitations of our scientific method: speed of light, Heisenberg uncertainty principle, Gödel's incompleteness of mathematics. How do those fit in this epistemological understanding?
Right. So one of the things that I should have said when I mentioned the ocean of the unknown is that in the ocean of the unknown, there are regions, let's call them that, of unknowables.
Uh-huh.
There are things in science that we just cannot know through the current scientific methodology, right? And Gödel's incompleteness theorem is pretty much a way of thinking about mathematics as not as a self-consistent closed system, but as something where you can ask questions about what is truth in this and that statement, and you cannot answer within that system. So what do? You enlarge the system, and then you try to answer, but then there'll be new ones, etc. Just like one of those Russian dolls, right? One inside the other, inside the other. And in cosmology, we can go back to this later, but the question of the Big Bang is one of them. The other one is a very, very concrete one, which is given that everything that we can know about the world depends on information that travels at the speed of light, and since the universe has existed for only a certain amount of time, which is 14 billion years, give or take, that tells you that along that time, life only traveled a certain distance, which means that we live in a bubble of information. And in principle, we cannot say anything about what's outside that bubble. So that's an unknowable. You can infer, you can speculate, but you cannot know. And I make a very clear distinction between these things.
Very important one. Okay, The Dawn of a Mindful Universe, a Manifesto for Humanity's Future. Recent book, 2023.
Yeah, so this just came out last year. Very different kind of book. It's really a book about the future of our project of civilization. How can we I basically got tired and sort of depressed by looking at all the dystopian scenarios for the future of humanity. And I kept asking myself, what it is that we can do in order to change this narrative. Is there a way in which we can coexist in a sustainable way with our planet? And as I thought about that, I realized that the answer to that is much deeper than we thought. Is really about how we define ourselves in relationship to our planet and to life. And once you start asking about that, you start asking about, well, what planet is this of ours, the planet Earth? And that made me dive into astrobiology and the connection between our planet and other planets and the possibility of life in other planets, to come back full circle to our Earth, to realize that this planet is a rarity in the universe, certainly in our galaxy. There will be very, very few, if any, similar to one. There will be no other planet like planet Earth, and there will be no other human beings in the universe either. And so I create, then based on those things, I create what I call a biocentric perspective, which basically means that every living world that sustains life is a sacred world and has to be respected, somewhat like indigenous cultures have respected our world, in a kind of like, we own our existence to this planet, and we cannot oversee or believe that we are above it. So it's a very different book, but it also brings in the pre-Socratics, the history, the religion, and of course, all the cutting edge science on other worlds, other planets.
Look, that's a very deeply spiritual idea with a small s, not a sectarian one, but a grand vision of the importance of life in the universe, and each life is unique in its own way. And we'll get into a discussion. Let's go right into the blind spot. First, a brief overview, and then I've got a lot of questions.
So The Blind Spot is a book that came out. I created an institute here at Dartmouth a few years ago that hosted scientists and humanists to talk about what I call the big questions. And we had together Adam Frank and Evan Thompson, the scientist and the philosopher, and myself. And they were here for a while, and we came up with this different way of thinking about science. We're not the first ones to point out that there is an issue about science being overly done, let's put it that way, that people become so enthusiastic about the successes of science, which of course need to be celebrated all the time, that they begin to consider science to be something that science is not. And to try to give to science a kind of God's eye view of the world, which we do not have and that we cannot have. And once you start to explore what are the consequences of giving this uber objective way of thinking about science and reifying reductionism as the way the world really is that it creates conceptual difficulties that we explore in the book in many different parts of scientific knowledge, from the notion of time and cosmology to our relationship to matter at the quantum scale, to the notion of cognitive neurosciences and consciousness, and also to planetary science. So in the book, we sort of break it down into different parts, and we explore what we call it the blind spot. And the blind spot is essentially the neglect that all scientific knowledge and everything that we do as humans begins with the experience of being in the world. So it's a sensorial connection before it becomes anything else.
Yeah, you have a very nice phrase in the book that I was looking for one sentence that can kind of compact everything that you've just said. And I think this is one. This is a quote, I think, that you're uncovering, that the blind spot is uncovering or remediating the blind spot is uncovering the primacy of direct experience in knowledge. Yes. And that subsumes all the things that you were saying, because that's all knowledge. So the primacy of direct experience. My initial reaction to that is that it's a wonderful idea. It's based on what we'd call continental or phenomenological kind of philosophy, which makes a great contribution. But again, my first reaction is that applies very significantly to the mental sciences, neuroscience, consciousness. It's central to that. It's very useful as a new way of thinking about biology. But once I get out to physics and time, I'm less convinced of its importance. So we'll be discussing that. What I'd like to do to begin, though, is you have a nice detail about segregating the concept of the blind spot in I think 6 different categories. And let me list the categories that you have in the book and just briefly describe it. So the first, and these are characteristics of the blind spot, and these are all bad things that inhibit our true understanding. So the first one you say is the bifurcation of nature.
Right. And the bifurcation of nature is the split between objective and subjective, is when we sort of confuse the fact that when we create a model of the world, right? So for example, I want to describe how the moon goes around the earth. So how do I do that? Well, I do that by saying, assume the moon and the earth are point masses, meaning they don't have any volume. They have different masses, and they are at a certain distance from one another. And they are attracted by a force, which is this force of gravity. And once I model things that way, I have this beautiful, extremely efficient way of describing the relationship between the earth and the moon, the orbit of the moon around the earth. And what the model, in order to be successful, it created all sorts of simplifications, right? Which are perfect for the Earth-Moon model. And the reason why this bifurcation happens and why it's important is because if you look at the history of science from Galileo onwards, you realize that most of the initial science was very objective. I mean, you could do this. You could separate an observer from an object very clearly. Galileo, when he was looking at the motion of penduli, that was okay because you're looking at the pendulum, it doesn't matter. Or when you're looking at balls rolling down inclined planes, which is the other thing he did to study free fall, that's all good. And Newton did the same thing by describing the motions of the planets with the force of gravity. Kepler, before Newton, did the same thing. So celestial mechanics dictated the early evolution of physics, and it is very good at distancing an observer from what's being observed. It's really immaterial, really. We don't care who is observing, right? There's the only experience that we have of all that is that, wait, in order to validate my theory, I need to go into the world and I need to, it's like Michael, hold on, let me turn this off. It's my printer making a weird noise. In order to validate my theory, I need to look at the world. And in fact, it started with me looking at the world because I saw the moon going around the earth and I wanted to make a model of that, right? And then, of course, so that's the beginning. Everything starts with, look, I saw that and I want to make a model of that.
Mm-hmm.
And then, because of the success of mechanics, early celestial mechanics and Newton's laws, it became more and more abstract. And you started to create structures like Lagrangians and Hamiltonians, which are mathematically more complex things that we use in mechanics to describe different kinds of systems. And slowly the level of abstraction started to become bigger and bigger and bigger.
Right?
Within mechanics, that doesn't matter that much because of this separation of observer and object. Maybe that's why you're talking about the blind spot in physics. However, when you start to move into areas of physics where this separation is not so obvious anymore, for example, quantum mechanics, where we know what to do, our models work very well, but the objectivity, the separation between the observer and what's being observed is all murky because of the uncertainty principle, that the act of observing affects what's being observed.
I want to get to quantum mechanics later because we're going to really focus on what I want to do now is go through the 6 areas.
Oh, sorry. Okay.
Yeah, no problem. We're gonna quantum mechanics to be a key area. I'm gonna really drill you on it, so be prepared. But let's go through the six. So bifurcation of
Oh,
nature is one, the objective and the subject. Second, reductionism. Use the term smallism, which is a nice micro reductionism. Reductionism versus other things. Emergence is again a prime theory, a prime theme of closer to truth. So we love reductionism. Reductionism is clearly epitomizes the blind spot.
yeah, because not every system can be broken down into its parts in order to be understood. There are some natural systems where you just can't do that, right? You cannot break a cell into its parts and hope to understand how a cell operates as a whole, right? A cell has a wholeness to it that if you tell me, oh, look, there is DNA in the nucleus and there is a mitochondria and there is ATP that does this or that, you're not understanding the cell anymore. You're understanding little chunks of stuff and not how the cell operates. And more complex systems in physics, the same thing happens, right? So there are emergent properties of systems that um, really go against this notion of reductionism. It's what Phil Anderson called more is different, which I think makes a lot of sense. So there are sort of more like layers of explanations that call for different concepts, and you cannot connect. So for you to tell me that, you know what, neurons are made of quarks and electrons, and that, yeah, but that's not going to help me at all understand how a neuron works, and much less consciousness. So
Right.
this line of physics is at the bottom of everything, and if I understand the physics, I understand everything else, is just false. So that's reductionism.
And that's reductionism within the blind spot. There are people who would argue for reductionism. It's a very complex subject. We can spend the whole time on it. You have to deal with concepts of emergence, whether it's weak emergence, which is predictable in principle from the physics, although you can't know it now, and maybe even never, but it is in principle knowable, versus strong emergence, where it's in principle not. Complicated subjects. There are people who still hold to that reductionism is real. It may not be you, it may not be me, but there are people we both respect who believe that. Third one is objectivism.
Right. And objectivism essentially is the notion that there is a world out there and that I can detach myself from that world in order to understand it completely. Right. And that just doesn't hold water, right? Because you can never detach yourself from the world, because the way we see the world is through our human perception of what's out there. And that's a point that we make a lot in the book as well.
Yeah, and look, and that's a very critical area. It's a wonderful area for discussion. Dan Dennett, who is a great mutual friend, would take the same data and argue the opposite, and says that it is true that there's this difference, but we can't trust our internal sense, that we can only trust the third person objective sense, even though there is this difference. So it's a very significant part of the blind spot in which there's different ideas. Physicalism, that everything is physical, again, has a similarity to reductionism in a sense, but describe it, please.
Well, yeah, I mean, it's a little different just in the sense that, yes, everything is matter, and hence, can we use physicalism to understand consciousness, right? So in the question of consciousness, is that all there is? And if that's all there is, then how do we make sense of consciousness? So that's where physicalism comes in.
I totally agree with that, 100%. I spent a lot of time thinking about that. Does that tension of physicalism within the blind spot apply anywhere else other than consciousness?
Um, depends who you talk to. If you talk to a panpsychic, right? People that
Okay.
believe in panpsychism, they say that the answer to the hard problem of consciousness is not just about human consciousness, but it's to kind of imbue the whole universe,
Sure.
sort of primordial or primals level of consciousness. And then you'd say that, yeah, that goes way beyond just human consciousness or any kind of consciousness.
If
So
there's reification of mathematics, you talked about a little bit earlier, but just give us a quick sense.
that is extremely important because it's what I called, even before the blind spot, I used to call that confusing the map with the territory.
Mhm.
And I think that's a very good way of explaining everything that we do in physics. They're all models. They're just mathematical equations that make very strong simplifications in order to describe a specific phenomenon or different phenomena, right? And because of the way they're constructed, they're only telling you part of the story. Perhaps the part of the story that we want to hear, which is I want to describe how this thing works. But we can never forget that the models are only part of the story, that the story itself as a whole cannot even be captured by our mathematics,
Mhm.
and that's where this comes in.
You use the phrase surreptitious substitution. Does that apply here?
Yeah, so I love that. So subreptitious substitution is Edmund Husserl's notion that we give, could also be called reification sometimes, that we make things which are ideas into realities, and we confuse the two things. So the concept of temperature, which we explore in detail in the book, temperature doesn't exist in a sense. We invented the notion of temperature after a lot of give and take that took centuries of understanding thermodynamics. What we do have is the sensation of hot and cold. That we have. From that primal sensation of hot and cold, we tried to explain what temperature was. There were like wrong ideas like caloric and other things until we hit on the notion as temperature as being related to the average kinetic energy of molecules of an ideal gas, which does not exist either. So because nothing is ideal, there is always an exchange of energy in collisions. So this separate, I think that is at the core of the blind spot, because once we become convinced that our models are real, we become emboldened to
Mhm.
kind of extrapolate them into areas that we have zero confidence that they hold. And that has put theoretical physics, especially cosmology and particle physics, into a lot of trouble in the last decade or more.
The last one, the sixth, is that experience is epiphenomenal. We have experience in all the sciences, but that is, as we say, the foam on the wave. It looks like it's doing something, but it just really for our entertainment, and it has no causative influence.
Um, yeah, so I'm not sure if that's so the way we look at experience, right? Experience is the sort of like starting point, the departure stage from where we react to everything else. So we talk about experience as being irreducible, like the sort of like there's nothing we can try to do to explain what experience really is. I mean, you can code it into, oh, this is coming from this part of the brain or from that part of the brain, and you see things because your visual cortex is being excited. But the experience itself, the way these neurons are coding what we see or hear or think or feel, we don't know how to deal with that, right? So that is connected to somewhat to the heart problem, but it's deeper than that. It's more than that. you
Yeah,
know
what I really like about the book is that many of these um, uh, problems with our understanding of science and understanding of reality comes from an appreciation of phenomenal consciousness. And then when we see the problem there, you're able to then apply it to other areas which are very creative and very stimulating to different kinds of thinking. Not sure I agree or not agree, but I had not thought of applying that same kind of principle in other areas. That's what I think is a major contribution of this book, forcing us to look at this problem we understand very clearly in one area, phenomenal consciousness, and seeing the application of some of the reasons we have a problem potentially to other areas. Major contribution. I have a couple of very quick questions to distinguish, if you will, the blind spot and its way of thinking, which is very original, to other kinds of theories that are extant. So let me just mention, I have three. One is what's called a social constructivist view of science, which basically says that science is relative. Science is relative by who has the power in the world. White men have power, so it's their science. I don't want to trivialize it because I think each of these views have very sophisticated understanding. So the blind spot is not that, right?
Not that at all. I mean, it's not attached to any kind of like social or political view in a sense, although you can always say that how can you really extricate, political and social and cultural context from the way science is actually performed or developed.
Right. That's its contribution. I agree.
So it's always part of a cultural context, right? And and what you could say, and I'm sort of agreeing with the social constructivism in a sense, is that what we have done by building this Western-centric scientific narrative, we have left behind other ways of knowing, other ways of thinking about reality in the world, which also have very valuable contributions to understanding, not just from indigenous peoples, but also Asian, ideas of science, or like Hindu science and old Chinese science, from the empire times, which we sort of like forgot about, but perhaps we shouldn't, because they enrich the way we describe the world. So I would say that the blind spot is not about that, but the blind spot has been, in a sense, created by the hubris of thinking that the Enlightenment way of the world, the Enlightenment is the way to deal with reality. Or it's the only way to deal with reality. So what the blind spot is doing really is offering a post-Enlightenment way of thinking about the world, which is also what I'm doing with the Dawn of the Mindful Universe. So the two books do have something in common that way.
Yes. Now, this is not at all what we call a radical empiricism, which says the only thing we can know is precisely what our experiments or observations say. We have absolutely no access, and in principle, to any sort of reality below. There are some similarities in terms of a questioning of the capacity of science to do something, but they come at it from two completely different directions.
Yeah. So I don't know if because I'm getting older, I'm getting a little more skeptical, but I mean, I did my PhD in string theory and worked in 10 dimensions and all that, which is something I wouldn't do at all now. But but I would say that yes, the way we do science, we have to be more careful about how we speculate, how we extrapolate our ideas too far away from experiments. And so I wouldn't say radical empiricism or experimentalism or instrumentalism is the only way to do this. But I would say that perhaps one of the symptoms of the blind spot is the excess of theoretical speculation over the lack of experimental backup.
And so that is, if we have a Venn diagram, that is a little bit of an overlap with the radical empiricist approach. So the next one is I had that this is not an anti-realist approach. And one very interesting, I think I got it right from the book, is that you said there's a blind spot in a realist approach and a blind spot in the anti-realist approach.
Yeah.
That both have elements of a blind spot.
Right, because I like to quote Democritus, the pre-Socratic atomist,
Yeah.
uh, who was so famous for suggesting that everything is made of these little bits of stuff. He actually said something that very few people quote, which is a shame, which is that in truth, reality is in the depth,
Mm.
which means what he really means by that is that the depth of what you mean by the fundamental nature of reality is an unknowable, that we just cannot figure that out. What we can do, and we have done beautifully, we can incrementally get to know better what's around us and how things operate. And that's the noblest kind of goal of science, but this idea that um, the idea that ideas can dictate the way we understand the world, I think I think is wrong. And I once a friend of mine once said that if you put 10 theoretical physicists in a room and they have never seen the world,
Mm.
and you say to them, okay, just figure out what the world is like, it would be all wrong. And so I think that that holds true. And of course you can also neglect our experience of the world in order to describe it.
Okay, Marcelo, what I'd like to do is now apply, as you do in the book wonderfully, the thinking of the blind spot to particular issues in science, and how the blind spot, or knowing that there is a blind spot, can help us understand it. And I want to focus initially on quantum mechanics. What you do really terrifically in the book is you list a number of the major theories of quantum mechanics, and then think about how the blind spot would affect each. Let me just list them so we can be sure to cover each one. The first is the classic importance of the observer, the so-called Copenhagen interpretation of you need some kind of an observer, whether it's a sentient observer or just a Geiger counter to collapse the wave function. One. Second is what you and I may think is a rather extravagant multi-world interpretation, where every the waveform doesn't collapse, but just branches into an innumerable or virtually infinite number of possible worlds in an exploding exponential sense. Third, you have is the hidden variables, pilot wave, something going beneath the surface that makes sense out of this. Fourth is relational, which our friend Carlo Rovelli has developed. And the fifth, which is a more recent one, which I find fascinating, I found it a bit bizarre, but fascinating, is cubism, if I'm pronouncing it correctly, a Bayesian approach, which I would have never thought would be relevant in quantum mechanics, where your prior understanding affects the probabilities involved. So go through, please, each of those from the perspective of the blind spot, and that how each of these theories, which have developed obviously independently of the blind spot, they're there in the world, but how the blind spot and the way of thinking can give new insights into each.
So quantum mechanics, right? Quantum mechanics is a good kind of a play field for exploring the blind spot, because quantum mechanics is one of those mysteries that we know how to use it, and it works so incredibly well to describe the behavior of small things in the world, but we have no idea how to interpret it. So, and then some people say that was the old tradition, said, who cares, right? I mean, physicists don't need to interpret anything. I mean, we just need to use things. That's sort of like the pragmatic approach. Do you so-called shut up and calculate kind of thing, right? Idea, which you know that's how we teach it, or most of it, not me, but most people that teach quantum mechanics would teach it that way. Say, look, it works. Don't ask too many difficult questions which are philosophical and would not bring any new knowledge to the story, which that's where the disagreement is. So in the Copenhagen interpretation, which is the original one, we have this thing called the wave function, which basically describes the probabilities of, for example, finding an electron in a given energy level around the hydrogen atom. And what it does say, and it's something that has extension, is a wave, right? And being a wave means it's not really describing what's happening at a particular point, but it's something that is spread out in space. So the electron is not even described by the wave function, which is kind of interesting. The wave function doesn't really have a physical interpretation, but its square, its absolute value, the absolute value of it, not because it's a complex quantity, but the square of it gives you the probability that you're going to find the electron in this level or that level once you make the measurement. So it's interesting because it's telling you probabilities now. So down with the determinism of classical mechanics. And it does tell you that once you make a measurement, the electron is going to be at a specific energy level in this example. And that's why you mentioned the collapse of the wave function. So what's wonderful about the Copenhagen interpretation is that it's all you need in order to use quantum mechanics. So if your focus is on, hey, I just want to use this stuff to calculate things and to explain results from experiments, it works really well. Built into it, there are all sorts of violations of certain laws of physics. For example, causality, because what it's basically being said here is that once you make the measurement, the wave function collapses instantaneously. And an instantaneous collapse of something that has extension in space has to be faster than the speed of light. And that's not good. So how do you interpret that, right? So you say, you know what? It doesn't matter. The wave function is not. That's Freeman Dyson's interpretation. I don't know why people get so worked up with quantum mechanics. You know, it just works, and the wave function is not a physical object. So that's the fundamental thing. Well, the blind spot there is that it is prescribing a way to deal with reality, which is not reality itself, because we don't know what reality itself is. So, but again, it works in a certain sense, right? I mean, it's efficient. And Niels Bohr tortured Einstein, you know, with this thing for many years. The second one you mentioned, I think, was the many worlds interpretation of quantum mechanics, which basically says, actually, who says the wave function is not a physical object? Let's assume the wave function is a physical object. It's called the ontic interpretation. And let's then say that once you make a measurement, you may see the electron here, but as you make the measurement, the universe splits into many parallel universes where all the other possibilities are also happening. So the wave function does give you all possible realities. It just happens that you are in one of them and not in the others. And I don't know what to say about that. I mean, I have very good friends of mine that, like Sean Carroll, who is a big many worlds person.
Right.
And I don't get it. I don't understand why that's such an appealing position to have, because it is populating the reality with all this parallel universe that, as far as I can tell, and David Deutsch and others say that there are other ways that we can do this, but I don't see how, that these universes are not reachable, you cannot confirm that. So it becomes just a metaphysical conversation, meaning you cannot empirically validate the many worlds interpretation. And in that sense, I don't see why that's so useful.
Yeah. Okay. Hidden variables.
And by the way, the blind spot here is to give reality to something that does not have it, which is the function.
Okay, that's
so
good.
That's a good one. What was the other one you wanted?
Hidden variables.
The hidden variables. Yeah, that is, a lot of the patriarchs of this whole thing, like de Broglie and Schrödinger himself and Max Planck, they're all big on the hidden variables. And then, of course, when David Bohm developed the theory, it became so exciting because it would show how the splits of probabilities actually happened because they were being guided by the so-called pilot wave. So it's adding a component to reality in order to explain something that we measure. The problem is, and here's the blind spot again, we cannot see this pilot wave. It is not part of a measurable reality. And the other thing that happens is that the way this is constructed asks for a simultaneous action of all of the universe, all of the matter in the universe, in guiding the behavior of the pilot wave. So everything is connected. That's why Bohm wrote a book called Wholeness and the Implicate Order, and wrote and exchanged beautiful conversations actually with Krishnamurti, because it was all about this interbeing, which is something that I actually love as a Buddhist concept. But in the case of physics, you can come up with that idea, but again, how do you know? And to me, physics is about how do you know? And there is a problem there, and that's the blind spot. Carlos, relativism. No, sorry, relational quantum mechanics. That one is the closest to what we kind of enjoy and like. And honestly, because what he's saying is that there are no things per se, but there are things in relationship to each other. So no object exists by itself because you would know it's there. The only way you have an object that exists is because it's being interacting with other things. You can say that about our brain too. You know, our brain is not a brain, it's a collection of many objects that are interacting with one another. And we know we exist because of these relationships and because you are there. So if you're there and I see you and I see me, then maybe I'm existing. So the relational is that interactions between objects are what dictate the way the world of the very small operates. And I'm very sympathetic to Rovelli's idea, right? I don't see, the only thing that I am a little concerned about is that it's still using, how can I put it? The observer is still playing a very important role in the sense of separation between me and the object, and that's where the relation comes from. You know, so there is a detachment there, so there is an objectivity in the formulation which is built into it. And finally, cubism. And you're right, cubism is strange. And I'm part of a discussion group with Chris Fuchs, which is one of the heads behind this thing, and Adam Frank too, and a bunch of other people. And the idea there is that cubism is the uber anti-blind spot of the interpretations of
right.
It's really about, look, you come into the world with a certain set of preconditions, so to speak, or visions of what reality is like. And the way you interact with your systems, the questions you're going to ask about the world are part of the answers they are going to give to how you see the world. So it's almost a social constructed way of thinking about quantum physics. You know, the good thing about it is that it really puts experience as the fundamental first step.
Yeah, it certainly does. It just seems, you know, it brings what David Lewis would say is an incredulous stare. When I first came across it, this is not the first time, but I came across it recently in another context. And you know, did I read that right? Where you know the prior belief system that you had affected what you see in a recursive process. But you know, as they say, it's not whether your theory is bizarre, too bizarre. It's whether it's bizarre enough to account for quantum mechanics.
Yeah.
Let's what I want to do in the last part, we talked about so much. After you have great commentary about the blind spot regarding time and life and mind. Wish we could go into all of that, but I'd like to focus a little bit on the origin of the universe and the cosmology, and I'd like to frame it with what is my prior about the creation of the universe, and then see maybe where my blind spot is, or what the blind spot can add to it, or if there's a different way. So if I look at models for the creation of the universe in its grandest sense, I would have four possibilities. The first is brute fact. To paraphrase Bertrand Russell in his wonderful BBC debate with Father Copleston, the universe is, and that's all. So it's a brute fact. Second, obviously, we have a supernatural creator, which many various religions would subscribe to, and many people. Third, a more recent vintage is, of course, the multiverse, an infinite number of universes with different laws, such that everything that's possible can happen, and must happen an infinite number of times, but forgetting that. And then that's combined with the anthropic principle, which says that only in those very, very, very few universes where sentient life could emerge from the laws of physics, would they emerge. And so it's not so special that we're asking about this, because it's only in this kind of universe could we even exist to ask the question. And so that's the multiverse, and that's motivated not just by the speculation, but by aspects of cosmic inflation, which would naturally seem to lead to that, or the string theory so-called landscape, which might lead to that as well. So that's the third. And the fourth is something to the effect that the universe has its own built-in causation, that there's a single universe that in a sense causes itself through a complex understanding of the quantum histories. It's not backwards causation, but it is things that happen at a future date, such as our consciousness, then kind of pre-selecting the quantum histories from the past. So the universe is participating in its own self-awareness or self-creation.
The origin of the universe. I mean, that to me is an absolutely fascinating question. My first book is called The Dancing Universe, and it's a book from a long time ago that I use here in a course I teach called Physics for Poets and Physics for Non-Science Majors. And it starts, first chapter is creation myth. It's about how way before science, how did people contemplate from different cultures the origin of the world? And I came up and I read hundreds of creation myths, and I came up with a classification of creation myths. There are only 5 possible solutions to the question of the origin of the universe. Okay, and the questions are organized like this. First one is there a beginning of time? Yes or no? So does the universe have a birthday or not? If you say no, that means the universe is eternal. That's Bertrand Russell. Mm-hmm. And there are 2 kinds of eternal universes. One where it's timeless, so it's always been there, it will always be there. It's like what happened with the steady state model in modern cosmology. And the other possibility is the universe had infinitely many expansions and contractions in the past. It's called and we'll have them in the future. It's kind of the Phoenix universe, expansion, contraction. So I love to say the universe is like a beating heart. Hmm. And every time you have this beating heart, you have a history of all the galaxies unfolding, etc. So, and that's the Shiva, the dance of Shiva, the Hindu myth, for example. Or the universe had a beginning. And then you have what we call an absolute cause, which is a God supernatural cause, which is your second example. Or you can have an origin out of nothing. The universe just came to be out of nothing by its own causation, which is your fourth kind of idea. And the Maori of New Zealand have a creation myth like that. Or the universe is a struggle between order and chaos, and emergence of order is what dictates the way the universe is. So those five possibilities are five possibilities that have been reappearing in modern cosmology in many different ways, and they're still present. The problem is, even if you have, again, a model of the universe, a model of the origin of the universe, like Stephen Hawking and James Hartle had this notion of,
No boundary.
no boundaries, the creation out of nothing. In order to do that, again, that is a model. How do you make models? You make assumptions. And what do you need? You need the concept of energy, the concept of space-time, the concept of conservation laws, the concept of fields, the simplification that you use in order to build a theory that you can actually solve mathematically. Those are the problems of subreptitious substitutions, where you create models that you believe are the way things are. And the problem is that no model can be complete that way, because you need a meta model. You need a way of explaining the universe had to be the way it is. And the multiverse is absolutely not the answer. The multiverse is the most exponentially blind spotted idea you can possibly come up with, because it's built on speculations of theories that we have no idea if they are valid early on in the universe or not. And I worked a lot on inflation and all what's called the reheating of the universe after inflation. And we just have to be honest about the fact that we don't know. So here's an idea, which some people say that's kind of like depressing, but I think it's actually very good, which is not every question you can ask needs to have an answer, a final answer. And in fact, I would say that in science, there are no such things as final answers. They're just the best answers we can give at a given moment in time.
Certainly agree with that. I wish we could go on. I would fight against that a little bit. I think there are answers. We might not ever know it, but the quest is what drives us and what drives humanity. And to me, the quest to deal with those questions, even if they are unanswerable, are a great unifier of all human beings.
That's why your show is called Closer to the Truth.
Yeah. No, it's not the truth. It's closer to truth without the...
Even better. Okay, closer to truth. Even better. Okay.
Thanks, Marcelo. That was great. I thoroughly enjoyed it. Frustrated we couldn't get into many more aspects of it, which I look forward to further conversations in the future. Viewers can watch dozens of TV episodes, hundreds of exclusive videos on cosmology, featuring many of the leaders in the field on the Closer to Truth website and the Closer to Truth YouTube channel. Thanks, everyone, for watching. Thanks, Marcelo. I look forward to our next conversation.
Yes, so do I. Let's have it. Thank you for having me.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.